Okay, continuing on. Um, One of the applications of differentials, aside from approximation, is in the propagation of error. So, let's say dy. This is the error in y. dy over y is the relative error in y. Therefore, dy over y times 100% is equal to the percent error in y. So, let's try this example. This isn't exactly a cube because we are given a bit, let's say this is the length, this is the width, and this is the height. The height is 32. And it says that the dB, this one by the way is a discrepancy. So it is said that this is the hypothesized dimensions. These are the measurements. However, there is a dB of 2 millimeters. These, by the way, are in cm. And for the dH, we also have 2 mm. So, applying these, that's when we get the actual measurements of the shape. There's a better term to call dB and dH. Let me just find that. Okay, so in this scenario, so this is a box, and the following dimensions was found to be 2 millimeters longer in all dimensions when measuring the box. So it appears to be that each side has to be 0.2 cm longer in order to meet the requirement that it has the actual size. So right now we want to approximate the volume of the box. So also we need to answer what the percent error is of the volume when compared to its supposed dimensions. So how do we compute? Let's just write down first our formula for percent error. Since we're dealing with volume, dV over V times 100 gives us our percent error. But first things first, how do we identify what our dV is? This is where we apply derivatives. For the actual or the volume that we can compute for right now, it's this. So let's do exactly that. V is equal to length times width times height. Okay. Six two five times 32. $20K. Okay, so that is the volume. Now we have to look for dV. We can actually solve this 3 ways. But but I'll show two of them. So we all know that the volume is length with height multiplication. But since length and width are equal, let's just say base squared times h. So what we can do, we can manipulate, because we want to express the formula this way. So we all know that the base is 25, right? And then the height is 32. At the other side, base over height. From there, manipulate 25h times 32. Sorry, 25h over 32 equal to b. Or 32 over 25b is equal to h. We can choose either of these two, but what I used was this. So proceed. Volume is equal to the base. We write that instead for the base. Squared times h. We can do that, or let me show you the other. 32 over 25b times b squared. So far so good. And from there, we find the derivative. So we could rewrite this as b cubed. So power rule, 3b squared times you place a constant here, 3b squared times du over dx. This du over dx is actually our dB, the error. So if we substitute, what is our dB from earlier? 0.2 cm. Let's just say 1 over 5. And when we simplify, 96. What is our base? 25, right? So 25 squared over 25 times 5. Cancel. 96 times 5. 480. So now that we're able to find dV, let's now use the formula for percent error. So dV is 480. Volume is 20,000 times 100. Apparently at least in my class, we weren't permitted to use a calculator, so you have to solve manually. 2.4%. So the percent error in the volume of this shape is 2.4%. That's one way to solve it. Another is through something called total differential. I'm supposed to introduce a lesson before this. It's called partial differentiation. I believe that if I teach that first, it would be more understandable. So I'll leave this scenario to you first. You don't have to know the other method.